Now that we've talked about covalent molecules, let's talk in a little bit more depth about the bond. So when we talk about a covalent bond, what we're talking about are electrons that are being shared between two atoms, and they can actually be shared in different ways. And one way is to have more electrons in between two nuclei and fewer electrons. So if we classify a single bond as two shared electrons, the length of that bond will be longer than if we have two bonds, which would be considered like 4 electrons, or a triple bond, which would be like having 6. So the reason for this is that the nuclei are positively charged and they repel each other. And the more negative charge that goes in between those two nuclei, the closer they can get to each other. So smaller atoms will make bonds with each other that are shorter, and then the larger the atom, the more distance there is between the two nuclei, because the larger atoms have a larger positive charge at their nucleus. So here we see two carbons, so everything is the same, like the pull and repulsion between the two nuclei, and then the pull for the nuclei and the electrons is the same because they're both carbon. Here we have a single bond, and that is 154 times 10 to the minus 12th meters, so picometers, and this would be 134 picometers and 120. So the other way we can classify a bond is by looking at something called polarity. So we call a covalent bond shared electrons, but sometimes they're shared evenly and other times they're shared unevenly. And so unless the bond connects two atoms of the same exact element, there's always going to be a slight difference. And if the difference is great enough, then you will see an uneven distribution of electrons that is consistent over time, so that you end up with something that has a pole because you have a more negative end and a more positive end. So a covalent bond that has equal sharing of electrons, like we have here with our two hydrogens, that is a nonpolar covalent bond. And here we have a covalent bond that has an uneven distribution, and we would call that polar. So it has a pole, a negative pole, and a positive pole, kind of like a magnet. So the way we can represent that is we use the lowercase delta to indicate a partial charge. So in this example, the hydrogen end would be partially positive because the electrons would spend significantly more time near the chlorine in this bond. And so that would be the partial negative or the delta negative. The other way we can represent this is with an arrow, and we put the arrow head pointing toward the negative end, which in this case is the chlorine, and then the tail is next to the positive end, which in this case is the hydrogen. So the way we know if a bond will be polar or nonpolar is to look at the electronegativity, which is a relative measure of how strongly atoms attract electrons to themselves in bonds. So fluorine, if it is bound to any of these elements, it's going to attract electrons more strongly because its electronegativity is a 4 on the Pauling scale. Oxygen's 3.5, so many things that are bound to oxygen would also make a polar covalent bond. And so we can use this simple subtraction to look at the difference between these values and then kind of decide if it's going to be polar or not. So if we look at no difference, so same atom, pure covalent, and then we can go up to an intermediate difference, and that would be polar covalent. And if the electronegativity difference is too big, it's really an ionic bond. So here is the guideline that we use. A pure covalent bond is 0.4 or less. So if it's the same atom, then it will be 0. And 0.4 is the carbon-hydrogen bond, and that is nonpolar. And anything that is smaller than that will also be considered nonpolar pure covalent. If it's between 0.4 and close to 2 somewhere. Some books will say 1.7, some will say 2, some will say 2.1. Those would all be considered polar covalent. So it's not really a hard cutoff at this end. And for our class, what we're going to use is we're going to say if it is a metal and a nonmetal, it is an ionic interaction. And we will only consider polar covalent bonds as those between a metalloid and a nonmetal or two nonmetals. So we don't have to worry about the upper limit here. If it's a metal and a nonmetal, it'll be considered ionic. So here's an example problem. So let's calculate the electronegativity difference between these elements and determine if the bond is pure covalent, polar covalent, or ionic. So if you want to stop this and do that calculation and come to your own conclusion and then check your work, that would be great. Okay, so we have HFCl, LiCl. So this here is hydrogen fluoride, chlorine, and lithium chloride. So the difference between hydrogen and fluorine is 4 minus 2.1. That's 1.9. This is about as polar as you can get without it being an ionic interaction. These are two nonmetals, so we would not call that a salt or an ionic compound. Chlorine, Cl2, since they're both the same atom, the difference would be 0. So clearly that is a nonpolar bond. And then lithium chloride, 2, it's also a metal and a nonmetal. So we would call this an ionic compound. So now without doing any calculations, let's see if we can decide what these compounds would be. So N2, nitrogen, this is 2 of the same atom bound to make the molecule. So that is going to be pure covalent or nonpolar. Carbon monoxide, this is 2 elements that have fairly different electronegativity. So that will be polar covalent. And magnesium oxide, this is a metal and a nonmetal. So this would be ionic.